So far, we have looked at what makes a good metric and what could be potential threat to its validity. Once you have solid metrics in place, you should start using them to answer the questions that you've defined in support of specific goals that you're trying to achieve. To do that, you will need to analyze the data. In other words, the metric values. There are 4 types of data analysis techniques, each with increasing complexity and value. The simplest one is called descriptive analytics. In the context of security metrics, this will likely be one of the most common techniques you are going to use, and the goal of descriptive analytics is to summarize and visualize data. For example, you might want to see average awareness scores for your employees or identify the lowest performers. Diagnostic analysis takes it a step further. It's about analyzing differences between groups and looking for correlations. For instance, you could check whether awareness scores are consistent across business units or whether some business units are performing better or worse than others. Predictive analytics is a powerful technique, especially useful in the context of awareness training, for instance. With this technique, you could predict outcomes like identifying vulnerable employee groups who likely need more training. It can also help you forecast higher risk periods for phishing attacks. By the way, AI in general and LLMs in particular are essentially predictive analytics models. Finally, prescriptive methods take things even further. For example, they might recommend specific training modules for employees identified as part of a vulnerable group. Under the hood, they use more complex models and aim to answer the question, what should we do based on what we've predicted? With that being said, I haven't really seen this technique used that much in practice, and for the context of security, you are going to stick mostly to descriptive analytics and sometimes perhaps diagnostic analytics. Let us have a look at some examples of these analytics methods, starting with descriptive analysis. Descriptive analysis is about visualizing your data to understand what's going on. There are many different ways to do this. You might start with simple averages and medians and move on to more advanced visualizations from there. For different metrics, you're likely to need different types of visualizations. And honestly, you should feel free to experiment here to establish certain patterns you're interested in. Here is a small example based on static measurement data. This could be, for instance, a representation of the scores from a phishing test. The left part of the chart shows a normal distribution. In other words, most participants score around the peak. On the right side, you see a distribution with 2 peaks. Interestingly, both datasets have exactly the same average, which shows that just looking at the average score is not going to reveal all the patterns that you might be interested in. The 2-peak pattern in this case might mean that you've got 2 distinct groups of employees, so it could be worth digging deeper to understand why. Let's have a look at another example. Here we're dealing with dynamic measurement data, so we use a line chart to track trends over time. The first chart at the top represents the number of incidents, for instance, for the past 200 weeks. In order to establish whether there is a trend upwards or downwards, we add a trend line to it, shown in the middle. And in this case, we see that the number of incidents is rising. Finally, the bottom part is taking a look at cyclicity. In this case, it seems that the incidents have a regular occurrence at regular intervals. For instance, it's a well-known fact that bad actors also enjoy their weekends off, so the timing might reflect on that. Diagnostic analytics is often used to figure out why something happened. It's great for comparative analysis between multiple groups, root cause analysis, and correlation testing. It also plays a key role in hypothesis testing, and here is a quick example to show what I mean. Let's say we've measured the response time across our organization for teams A and B. Using descriptive statistics, we find that team A's average response time is 42 minutes, and team B's average response time is 48 minutes. So the question at this point we are interested in answering is whether Team A is actually faster than Team B. But here's the catch. In data science, you can't answer that question just by comparing the averages. You can't even answer it just by looking at the data points. This is where diagnostic analytics come in. You need statistical methods that account for variability and noise to determine whether these observed differences are real or just due to random chance. The proper way to approach this comparison is through hypothesis testing. In a nutshell, our hypothesis is that Team A is faster than Team B. That's what we suspect based on the average response times and the descriptive analysis. But in data science, we don't prove things directly. Instead, the standard approach is to disprove the opposite, which is called the null hypothesis. So in this case, the null hypothesis is that teams A and B have similar response times. In other words, there is no meaningful difference. And now we're going to use statistical methods to try to disprove the null hypothesis in favor of our original hypothesis. I won't go into the details of the t-test here, since that will take us a bit too far. But in our previous example, it turns out that the difference between teams A and B wasn't statistically significant. In other words, we can't confidently say that team A is faster, at least not based on the available data. Finally, we get to predictive analytics. As the name suggests, these methods are all about forecasting. They work by defining a dependent variable. That's the thing we're trying to predict. For example, let's say we want to predict a person's security awareness score. Next, we identify a set of predictors or factors that might influence or help predict that outcome. In our example, we could use predictors that are training engagement or training frequency, tenure, how many years has that person been within the company, role, number of phishing attempts that he or she has reported, access level, and maybe other predictors. Once we have those, we start building a predictive model. We do that using statistical or machine learning techniques. However, I won't go any deeper than this, as this matter is a whole course on its own. The key idea is that predictive analytics helps you anticipate outcomes before they happen, so you can act proactively. Let's bring it all together using our running example. Our goal is to increase security awareness of our employees. The two questions that we have defined in support of that goal is: what is the current security awareness? And what is the trend in security awareness? We start with descriptive analysis of a metric that we've defined, the security knowledge assessment score, which we have established using a quiz. Looking at individual scores, we're going to compute mean values, spot trends over time, look at averages. Ideally, we'd see scores improving as awareness increases. Then, using diagnostic methods, we compare different teams. Are some teams consistently doing better than others? If so, we might identify groups or individuals who need additional training. Finally, using predictive methods, we can go one step further and build a proxy awareness score. That gives us a second model-based metric we can use to predict awareness based on things like training frequency, tenure, and access level.